The next type is called the Factor Theorem. When it seems none of the methods explained so far will apply to a given expression, perhaps the Factor Theorem method will. Consider the polynomial of one variable. A simple extension of this method will also apply to a polynomial of two variables, but we will do that later. If we have a binomial divisor, into a dividend, the result is a quotient and possibly down here a remainder. Therefore, it follows that divisor multiplied by the quotient plus the remainder equals the dividend. Now, if the remainder is 0, then we have the factors called the divisor multiplied by the quotient, which would equal the dividend. In other words, if the dividend was a trinomial that was factorable, then it would factor into a binomial divisor here and a binomial quotient. This multiplied by this is equal to the dividend, and there would be a 0 remainder. All of the parts are polynomials. Let us assume that the binomial divisor is equal to x plus p. Multiplied by the quotient equals the dividend, where p is some number. If the left side equals 0 when x is substituted for a given number, so will the right side equal 0. If the left side equals 0 when x is substituted by a suitable number, the right side will equal 0 also. Now, the suitable number happens to be minus p for x. That suitable number for x happens to equal to minus p. In other words, the opposite in sign value of the number that p is supposed to represent. Well, how is this true? Well, if you take minus p and put it where x is, minus p plus p times the quotient equals the dividend, it's easy to see that negative p plus p equals. So if we substitute the negative value p for x on the left, and this causes, then x equal to minus p will also make the dividend value vanish when that substitution is made and the polynomial is simplified. And that is basically the so-called factor theorem. Let me illustrate this with an example now. The procedure is actually one of a method in trial and error, because you have to sort of try a value of p into the given polynomial to find out if it vanishes or not, and if it doesn't with a selected value, then you must try another value. What we normally do is choose simple numbers like minus 1 plus 1, minus 2 plus 2, and minus 3 plus 3, etc. Your problems will be so designed that these numbers substituted into the polynomial will always work. So here we have an example then. Factor x cubed minus 2x squared plus 1. I happen to know that this polynomial can be factored. You cannot factor this polynomial in any of the methods so far described. Let's test then by letting x equal to minus 1. You see, that's the same as saying let x equal to p in the theorem that I described earlier. When x is equal to minus 1, the result is minus 1 cubed minus 2 times minus 1 squared plus 1. The amount is negative 1, negative 2, plus 1, and that does not equal to 0. So the test fails. Well, try x equal to positive 1. If x equal to positive 1, we have 1 cubed minus 2 times 1 squared plus 1. This is equal to 1 minus 2 plus 1, and that does equal to 0, so we end up with the test working. When x is equal to 1, then, we conclude that x minus 1 is a proper divisor. We now use long division to find what the other factor is. The other factor will be the quotient when x minus 1 is divided into the given problem. So we write, we conclude here that therefore x minus 1 is a factor, and continue by saying x minus 1 then divided into x cubed minus 2x squared plus 0x plus 1. If you don't understand why the 0x's, x divided into x cubed is x squared. Multiply this out. Subtract. Bring down a number. X into minus x squared is negative x. We have negative x squared, positive x subtract. We have negative x plus 1. X into that is minus 1. And when we finish this off, the remainder is 0, as we expected. If this did not equal to 0, you would get a remainder, as the theorem explains. The factors are x minus 1 multiplied by x squared minus x minus 1. Here is another example. Factor x cubed minus 2x squared minus x plus. Now you might think this is a candidate for the factor theorem method. So be careful with questions such as this one, which can be solved. It can be solved by using the factor theorem, but it's much simpler to solve by grouping. Notice that if I group the first two terms together and the last two terms together, that this is equal to x squared times x minus 2 minus x minus 2, and that x minus 2 is a common factor to both of these terms, leaving x squared minus 1 behind. This follows with x minus 2 multiplied by x minus 1, x plus 1.